Imagine you are standing inside the kitchen of a really big global fast food chain, and it's the busiest hour of the day.
Oh, yeah, pure chaos.
Right. Orders are flashing on the screens everywhere. The cooks are rapidly making burgers. Cash registers are opening and closing like every single second.
It's all moving so fast.
Exactly. Everything in this environment is built for extreme speed. It's all about the present moment. If the computer system stops working for even 1 minute, the company loses real money.
Yeah, they lose money, and they definitely lose angry customers. And I mean, that is exactly how most normal computer databases work today.
Just focusing on the right now.
Right. They are designed to handle thousands of small instant events, but they have a major blind spot. They just do not have time to think about the past.
So if you walk into that really busy kitchen and ask the manager, hey, how many cheeseburgers did you sell on rainy Tuesdays in Europe over the last 5 years?
The manager would probably tell you to leave the kitchen.
Yeah, the whole system would just completely freeze. It cannot answer that question.
No, it can't. To answer a big question like that, you have to leave that loud kitchen completely. You have to walk into a completely different building.
Like a library. Imagine a giant, perfectly quiet mega library.
I love that analogy.
This library holds a perfect historical record of every single burger the company ever sold. It knows the exact time, the exact customer, the weather that day, and the price.
And if this quiet library stops working, a massive company cannot tell if it is actually making a profit or if it's going bankrupt.
And that quiet, powerful library is what we call a data warehouse.
Exactly. It is basically the brain of the modern business.
Behind every online store you use, every bank where you keep your money, and every social media app on your phone, there is a data warehouse, silently organizing millions of pieces of information.
Which is why we're talking about it today.
Welcome to today's Deep Dive. Today, we are looking at a really fantastic, detailed guide from DataCamp. It is called the Top 51 Data Warehouse Interview Questions and Answers for 2026.
It's a great list. It covers so much ground.
It really does. Our mission today is to open up this ultimate cheat sheet. We are going to explore exactly how this giant library is built, how it works, and how data engineers manage to keep it running without breaking everything.
Yeah, this material is incredibly valuable for the listener. The guide doesn't just list boring facts. It shows the real problems companies face when they try to manage, massive amounts of information.
Now, before we really jump in, I need to make a very clear promise to you, the listener. Today's deep dive is a little bit special.
Very special.
The world of data architecture is usually full of very complicated, advanced jargon. It can easily sound like a foreign language.
It really can, even for people in tech.
Right. But today, we are going completely back to basics with our language. We're going to use clear, simple English. Specifically, we are sticking to B1 level English vocabulary and grammar.
Which is a great challenge for us.
Definitely. We will not use any confusing technical words without giving you a simple, real-world explanation first. We are going to explain highly complex systems using plain, everyday words.
I fully agree with this approach. I mean, complex ideas do not need complex words. If we cannot explain a computer system simply, well, it probably means we do not truly understand it ourselves.
So true. So whether you are preparing for a massive tech interview, or maybe you just want to understand what your data engineering team actually does all day.
When they're just staring at their screens, typing.
Exactly. Or maybe you are just curious about how global companies manage to remember every single thing you buy. Whatever your reason is, this conversation is designed for you.
So where do we start?
Well, let's unpack this. We have to start with the absolute foundation. Before anyone can pass a job interview, they need to prove they know the basic building blocks of the system.
Yes, you have to prove you understand the basic difference between the kitchen and the library.
In technical terms, the guide asks people to explain the difference between OLTP and OLAP.
Let's break those letters down.
Okay, OLTP stands for Online Transaction Processing. The key word there is transaction.
Right. So when you use your credit card to buy a $20 red shirt at a store in London, that single action is a transaction.
Just one simple event.
Precisely. And OLTP systems are built to process that exact transaction instantly. We call this kind of system write-heavy.
Write-heavy, meaning it writes new data a lot.
Exactly. Its main job is to write new information into the database as fast as possible.
Yeah.
You want your bank balance to go down by $20 the exact second you buy that shirt. You do not want to wait 10 minutes.
Oh, no. That would be terrible. But then we have the library, OLAP, which is Online Analytical Processing.
Yes, and the key word there is analytical.
which basically means studying things deeply to find patterns, right?
That's it. And this is where the data warehouse lives. OLAP is not write-heavy. It is read-heavy.
So it spends its time reading data, not making new data.
Right. Instead of writing one tiny new transaction, an OLAP system is designed to read millions of old transactions all at once. It scans years of history to answer really complex questions.
Like calculating the total profit for all red shirts sold in Europe over 3 entire years.
Exactly. That requires reading a lot of history.
So an OLTP database handles the instant reality of right now, the kitchen, while an OLAP data warehouse handles the deep analysis of the past, the library.
That makes perfect logical sense.
Okay, so now we are inside this massive library. The information has to be organized on shelves somehow. The guide talks about 2 main types of tables used to store data: fact tables and dimension tables.
Yes, this is a huge part of any data interview.
Let's trace my $20 red shirt. Where does it actually go?
Well, if we break it down, a business event has 2 parts. You have the numbers and you have the context.
Okay, numbers and context.
A fact table holds the numbers. It holds the measurable facts of the event. For your purchase, the fact table simply records the number 20 for the price and the number 1 for the quantity.
Just numbers, but numbers by themselves are completely useless.
They really are.
I mean, a row in a computer that just says 20 and 1 tells the business absolutely nothing.
Which raises an important question. Who bought it? When did they buy it? Where did they buy it?
Oh, I see.
That is the job of the dimension tables. Dimension tables hold the descriptions. They hold the actual text.
So the dimension tables hold the story.
Beautifully said. Yes.
One dimension table holds the customer details, so it says my name. Another dimension table holds the location, so it says London. And another holds the product detail, so it says red shirt.
Exactly. So when a business analyst wants to create a report, the computer joins the fact table to the dimension tables. It links the numbers to the story.
That brings up how we actually arrange these tables together.
Yeah.
Engineers call this a schema, like the blueprint of the database.
Right. The schema is the design.
The guide contrasts 2 main designs, the star schema and the snowflake schema. Now, a star schema sounds very visual.
It is very visual. If you draw it on a whiteboard, you put your single fact table directly in the center. The numbers are right in the middle. Then you place your dimension tables around the outside, pointing directly into the center. It literally looks like a star.
Because it is a simple shape, I imagine the computer can read it very quickly.
Yes, that's the main benefit. A star schema is highly optimized for fast reading. The computer only has to make one single jump from the center fact table to any dimension table.
One jump is fast, but there has to be a negative side.
There is. It creates a specific problem with storage. It forces the system to record a lot of redundant or repeating data.
Wait, what do you mean by repeating data?
Let's say 1 million different customers buy a shirt in London. In a star schema, the system has to write the words London, United Kingdom, Europe, 1 million separate times in the location dimension table.
1 million times. That seems incredibly wasteful.
It takes up a lot of space. Now contrast that with the snowflake schema. Think about a real snowflake. It has many small branches splitting off from larger branches, right?
Yeah.
In a snowflake schema, you break those dimension tables into even smaller separate tables.
Walk me through how that works for London. I want to picture this.
Okay, instead of writing London, United Kingdom, Europe in one big table.
Which takes up a ton of space.
Right. Instead, you create a tiny table just for regions containing the word Europe. You link that to a table for countries containing United Kingdom, and you link that to a table for cities containing London.
Okay, let's unpack this, because here is where it gets really interesting for me.
Okay, go ahead.
In the year 2026, computer storage space is incredibly cheap. I mean, you can buy massive hard drives for almost nothing.
Very true. Storage is cheap.
And you just said that a star schema is much faster for the computer to read.
I did.
So if a snowflake schema makes the computer jump through 3 different tables just to find out a store is in Europe, which slows the whole thing down, why would any company choose a complex snowflake schema? I mean, why do we care about saving a few gigabytes of cheap storage space?
You have identified the core debate in data architecture. It's a great question. But what's fascinating here is that the snowflake schema is actually not primarily about saving money on storage space.
It's not.
No. It is about something called data integrity. It is about preventing silent corruption.
What do you mean by silent corruption? That sounds scary.
Well, imagine that the political boundaries change and a city is moved to a different region, Or simply, someone realizes United Kingdom was spelled wrong in the system.
Oh, I see where this is going.
In your star schema, that text is written 1 million times. You have to find and update 1 million individual records. If the computer misses even one single row, your data is now broken and inconsistent. Your reports will be wrong.
Ah, I understand now. In a Snowflake schema, the words United Kingdom only exist in exactly one single row in that country table.
Right.
So if I need to fix the spelling, I just change one row, and the entire database is instantly and perfectly updated.
You hit the exact benefit. It minimizes data redundancy. It trades reading speed for perfect, absolute control over the consistency of the data. And large enterprise systems often require this level of strict control.
So we have the blueprint. We know if our shells are shaped like a star or a snowflake, but, an empty library provides no value.
Yeah, you need books on the shelves.
Exactly. We have to move millions of records from the noisy fast food kitchens of the real world into our quiet library. And moving this data is incredibly difficult.
It is the hardest part of the job.
Which brings us to the plumbing of data engineering. The Data Camp Guide spends a lot of time on ETL versus ELT.
Yes, the ingestion process, how we actually get the data into the system. ETL is the traditional process that companies have used for decades. The letters stand for extract, transform, and load.
Let's break those down for the listener. Extract means pulling the data out of the original source.
Correct. You connect to the sales database, the marketing website, and the customer service software, and you copy the data.
But raw data from the real world is incredibly messy, right?
Oh, it is terrible. It contains missing fields, spelling errors, duplicate records. If you just drop that raw data into your warehouse, you will completely ruin your clean library.
So the next step is T-transform. How does transformation work? I like to use industrial analogies. Is it like a water filtration plant?
That is a very accurate analogy. In ETL, you extract the muddy water from the river. But before the water ever reaches your final clean storage tank, you pass it through a separate filtration building.
Oh, a separate building.
Yes. You use a specialized server to clean the data, you filter out the duplicates, you standardize the dates so they all look exactly the same, and you format everything perfectly.
And then finally, the L load. You pump that perfectly clean water into the final data warehouse tank, extract, transform, load.
Exactly. For a long time, tools like Talend and Informatica were heavily used to do this separate transformation work.
But things have changed, right?
A lot. The guide highlights a massive modern shift in the industry. Today, most modern data teams use ELT, extract, load, and then transform.
Wait, extract the muddy water, load it directly into the final clean tank, and transform it inside the tank.
That is what it means.
That sounds like a terrible idea.
Yeah.
Aren't you just building a giant garbage dump inside your beautiful data warehouse?
It does sound dangerous,
Yeah.
but if we connect this to the bigger picture of modern technology, it makes perfect sense. Modern cloud data warehouses like Snowflake or Google BigQuery have unimaginable computing power. They are supercomputers.
Okay.
It is actually much faster and cheaper to load all the raw, dirty data into a specific, isolated corner of the warehouse and then use the warehouse's own massive brain to clean the data.
Oh, an isolated corner. So you don't drop the dirty data onto the main reading shelves where the business analysts are working?
No, never. You load it into what engineers call a staging area. Think of it as a quarantine zone or like a mud room at the front of a house.
A mud room. I like that. You take your dirty shoes off there.
Exactly. The data enters the mudroom. Then, the powerful warehouse runs heavy SQL code to transform, clean, and test the data right there. Only when it passes every single quality check is it finally moved to the production tables.
ELT uses the power of the cloud. That is a brilliant design. Now, once the data is inside and clean, the warehouse starts growing. We get millions, then billions of rows.
It gets very big, very fast.
And if I ask a question, the computer cannot possibly read billions of rows one by one. The guide discusses two specific techniques to find data fast: partitioning and indexing. Let's talk about those.
Both techniques are essential, but they work in very different ways. Let us start with partitioning. This is usually about physically dividing the data into smaller, logical blocks. The most common type is horizontal partitioning by date.
So instead of throwing 10 years of global sales data into one giant digital box, the engineer programs the system to create a separate box for each month of each year.
Yes. So when your CEO asks, hey, what were our sales in March 2026? The database engine does not even look at the other box.
It just ignores them.
Completely. It ignores a decade of data and only opens the one box labeled March 2026. It cuts the amount of work down by 99%.
That makes the process incredibly efficient. And how is indexing different from that?
Think of a real physical book. If you want to find every page that mentions the word encryption, you do not read the entire book from page 1, right?
Right. I would go to the back of the book.
Exactly. You look the index, you find the word encryption, and it gives you a tiny shortcut list of exact page numbers.
So an index in a database is literally just a shortcut map.
That's all it is.
Partitioning organizes the actual data into big chunks,
Right.
while indexing creates a separate map that points to specific individual rows.
You have the exact mechanism. Now, to make all these tables and indexes work together, the data needs identification numbers. And this introduces a very specific rule from the guide:
Which rule is that?
the use of surrogate keys instead of natural keys.
Okay, I want to make sure I understand this. A natural key is a real-world identifier, something that naturally exists. Like, for a citizen, it might be a national identity number. For a car, it is the vehicle identification number. For a product, it is the barcode.
Yes, those are natural keys. And in a poorly designed system, a beginner engineer might use that real-world barcode as the main link connecting the fact tables to the dimension tables.
But the guide says we should never do that. Instead, the warehouse should generate its own fake sequential numbers, like product 1, product 2, product 3. And these fake numbers are called surrogate keys.
Correct.
Why go through the trouble of inventing new numbers when the real-world barcode already exists?
Because the real world is chaotic and unpredictable. Natural keys change
Really? A barcode changes.
all the time. Let us say a massive company buys your supplier and they decide to completely change the barcode format for all products. If your entire historical library is tied together using those old barcodes, your system will just break.
Oh, wow. So if my customer, let's call her Sarah, changes her legal last name, and her name was the natural key holding her 10-year purchase history together.
The moment you update her name, the connection to her past purchases is completely destroyed.
That is terrifying.
It is. But if Sarah is secretly just customer number 8475 in the background system, a surrogate key that the database controls and that never ever changes, she can change her name, her address, her phone number. The real-world data changes, but the structural link remains completely unbroken.
It protects the database from the chaos of the real world. That's incredibly smart. It creates a stable internal reality.
Exactly.
But, that concept of people changing their details brings us perfectly to the next major challenge. The guide calls it intermediate concepts, but it is really about the messy reality of time travel.
Time is definitely the hardest variable in data engineering.
Why is it so hard?
Well, in a simple app, if a user updates their profile, the app just saves the new information and forgets the old information. But a data warehouse is a historical library. It cannot just forget.
Right. The guide introduces a highly technical term for this: slowly changing dimensions, or SCD. Let's explore how a warehouse handles a dimension, like a customer's location, that slowly changes over time.
Let's use our customer, Sarah, again.
Okay, Sarah currently lives in New York. The business records this. But today, she gets a new job and moves to Los Angeles. How does the database handle this update? The guide lists 3 different SCD strategies.
Let us start with SCD Type 1. This is the simplest method. In Type 1, you simply overwrite the old record. You delete New York and you insert Los Angeles.
But wait, if I delete New York, the library loses its memory.
Yes, it does.
If the marketing team looks at Sarah's purchases from 3 years ago, the system will say she bought those items while living in Los Angeles. But she didn't. The historical context is completely destroyed.
You are absolutely correct. Type 1 destroys history. Therefore, an engineer only uses Type 1 when the history does not matter to the business or when they're correcting a simple mistake.
Oh, like a spelling error.
Right. If her name was misspelled, you use Type 1 to overwrite it. You do not need to preserve a historical record of a spelling error.
Okay, but what if the business demands perfect history? What if the analysts need to know exactly where Sarah lived during every purchase she ever made?
Then the engineer must use SCD Type 2. This is the most common and powerful method. In Type 2, you do not delete or overwrite anything. When Sarah moves, you create a brand new second row for her in the dimension table.
So the table now has 2 separate rows for Sarah. How does the computer know which one is current?
By using date columns, the first row will say, Sarah, New York, valid from January 2020, valid till today.
Okay.
The second new row will say, Sarah, Los Angeles, valid from today, valid till December 99,999, which just means it is the current active row.
That is literal time travel. If an analyst asks, hey, where did Sarah live on March 5th, 2023? The computer checks the dates, ignores the Los Angeles row, and pulls the New York row. It reconstructs the exact truth of that specific day.
Yes. Type 2 perfectly preserves the timeline. Now, there is also SCD Type 3. This is a compromise.
How does Type 3 work?
In Type 3, you do not create a new row. You keep the single row, but you add a new column. You have one column for current city showing Los Angeles, and one column for previous city showing New York.
So I think I just logically figured out the problem with Type 3.
Oh, what is it?
What happens when she moves a third time to Chicago?
The system overwrites the columns. Current becomes Chicago, previous becomes Los Angeles, and New York is deleted forever. Type 3 only remembers one step backward. It cannot store a deep history.
So let's unpack this. If Type 2 is the only method that preserves absolute perfect history, why would an engineer ever use Type 1 or Type 3? Why not just use Type 2 for absolutely every single column in the entire warehouse?
This raises an important question about system limits. Think about a global platform with hundreds of millions of users.
Like a big social network.
Exactly. Users constantly change their app settings, their profile pictures, their notification preferences. If you create a brand new row in your database every single time a user clicks a minor setting, your dimension tables will explode in size. They will grow from millions of rows to billions of rows in a few months.
And as we discussed earlier, even with good partitioning, forcing the computer to scan billions of unnecessary rows will make the daily reports take hours instead of seconds.
Precisely. Data engineering is a constant negotiation between perfect historical accuracy and system performance. You only implement the expensive Type 2 logic on data that the business actually needs to track over time, like geographic location or subscription level.
That balance is fascinating. Now, speaking of adding new data over time, how do we actually run the daily updates? The guide talks about incremental loading.
Well, you cannot reload the entire historical library every single night. If you have petabytes of data, it would take weeks to load. You must only load the new data, you only load the increment.
How does the ingestion tool know which rows are new and which ones are old?
The guide highlights a few mechanisms. The most standard way is using timestamps. In the source database, every row has a column called last updated.
So it knows the exact time it was touched.
Right. At midnight, the ETL tool simply asks the source, please give me all rows where the last updated time is greater than yesterday at midnight.
It seems very straightforward.
It is, assuming the source database developers actually included a timestamp column.
What if they didn't?
If they did not, engineers use something called change data capture, or CDC.
How does CDC work without timestamps?
It operates at a deeper system level. Every database keeps an internal hidden log file of everything it does, just in case it crashes and needs to recover.
Like a diary.
Exactly like a diary. A CDC tool acts like a security camera watching this hidden log file. Every time a cook in the fast food kitchen inserts a new burger sale, the CDC tool immediately reads the log and streams that specific change to the warehouse.
Wow. So CDC does not even ask the database for the data. It just quietly reads the database's internal diary. That is incredibly clever.
It is very efficient. But what happens if you cannot use timestamps and you are not allowed to use CDC? The guide mentions a final brute force method, snapshot comparisons.
Brute force. That sounds heavy.
It is very heavy. You take a full digital picture of the entire source table yesterday. You take a full picture today. Then you force the warehouse to mathematically compare every single row of both pictures to find out what changed.
That sounds like it would take forever.
It consumes massive amounts of computing power, but it guarantees you find every single change.
Okay, so we are loading data incrementally. We are tracking history with SCD Type 2. But what happens when the very structure of the business changes? The guide covers schema changes.
This is always a stressful time for engineers.
Let's say our clothing company suddenly decides to start selling shoes. The analysts demand a new column for shoe size in the main table. Can the engineer just quickly add a column?
Absolutely not. In a massive data warehouse, adding or renaming a column is a major event.
Why? Just one column?
If an automated dashboard or a machine learning model is expecting exactly 10 columns and you suddenly give it 11, the entire pipeline might crash.
Oh, I see. So what is the safe process?
The guide states you must perform an impact analysis. You have to trace the data downstream. You find out exactly which reports depend on that table. Then you use schema versioning.
Versioning, like software versions.
Exactly. You do not alter the live table. You build table version 2 with the new shoe size column. You slowly move the analyst to version 2 while keeping version 1 running for the older automated systems. It is like replacing the engine of a car while it is driving down the highway.
The level of caution required is immense. But this brings us to the operational reality. What happens when things actually go wrong?
Because they always do.
Right. The company goes viral, sales explode, and suddenly the CEO is angry because the daily revenue dashboard takes 20 minutes to load.
This is a classic scaling problem. The volume of data has outgrown the design of the system.
The guide offers a few solutions. We already talked about partitioning the data by date. But there is another major concept here. Materialized views. This is a very specific technical term. What is a materialized view, and how does it speed up a dashboard?
Let us break down the words. In SQL, a normal view is simply a saved question. It is a piece of code. If you create a view that calculates total global sales, every time you open that view, the computer has to run the code.
So it has to scan millions of rows and do the complex math every single time.
Yes, and if the math takes 20 minutes, you wait 20 minutes every time.
That is extremely inefficient. If 10 different executives open that dashboard every morning, the computer's doing the exact same heavy math 10 times.
Exactly. This is where a materialized view changes everything. A materialized view does the math once, and then it physically saves the final answer on the computer's hard drive. It materializes the data.
Oh, I get it. It is like doing your meal prepping on Sunday. You cook all the food and put it in a box in the fridge.
Yeah.
When you are hungry on Tuesday, you do not cook from scratch. You just open the box. It takes 1 minute.
That is the exact mechanism. When the executive opens the dashboard, the system does not calculate anything. It simply reads the pre-calculated answer from the hard drive. The dashboard loads in milliseconds.
But wait. If I think about this logically, if I am meal prepping on Sunday, the food I eat on Thursday is a little bit old.
Yes, it is.
If a materialized view is just the saved answer from yesterday, isn't the executive looking at old data? What if a massive sale happened 5 minutes ago? The answer saved on a hard drive doesn't know about it.
You have identified the exact trade-off data engineers struggle with daily. You are completely right. A materialized view is only as fresh as the last time you ran the math. You are explicitly trading real-time freshness for extreme reading speed.
So how do you fix the freshness problem?
You set up automated refresh schedules. You program the warehouse to say, hey, every 15 minutes, quietly recalculate the math in the background and overwrite the saved answer.
Oh, okay.
Some advanced systems can even do incremental refreshes, where they only add the new 15 minutes of sales to the old total without recalculating the past 10 years.
Okay, that makes sense. Now, another disaster scenario in the guide is high data latency. Latency is a B1 word that basically means delay.
Yes, a delay in the data arriving.
The CEO is complaining that Tuesday's data is not showing up until Thursday. The ingestion pipeline is just too slow.
When dealing with high latency, the engineer must identify the bottleneck. Where is the water getting stuck in the pipes? If they're using old ETL, the transformation server might be overloaded.
So they might switch to ELT, pump it straight into the big warehouse, and use the giant compute power to clean it faster.
Yes. Or they might completely change the architecture to use stream processing. Instead of loading data in huge, slow batches once a day at midnight, they use a tool like Apache Kafka.
How does Kafka help?
Kafka streams the data continuously. Every time a single transaction happens in the kitchen, Kafka sends that single record into the warehouse immediately. It converts a batch process into a continuous flow.
That would definitely reduce the delay. But what about the worst disaster of all? The guide calls it data discrepancies. Let's just call them data errors.
They are a nightmare.
The marketing software reports 1,000 new users, but the data warehouse dashboard says there are only 800. The numbers do not match.
This is a crisis. If the business cannot trust the numbers in the data warehouse, the entire system loses its value. When this happens, the engineer must act like a detective and trace the data pipeline backward.
How do you trace it?
You start at the end, you check the reporting tool. Is the dashboard using the correct SQL query? If yes, you step back to the transformation stage. Did the cleaning code accidentally filter out 200 legitimate users because their email format was strange?
And if the code is fine?
You step back to the extract stage. Did the ingestion tool fail to connect to the European server? You find the broken link in the chain.
Okay, so you find the problem. Then what?
You fix the code, you backfill the missing data to repair the history, and then you do the most important thing. You communicate. You explain to the business leaders exactly why it failed and how you have added new automated tests to ensure it never happens again.
Communication is critical.
Mm.
And, executing all these tasks requires knowing exactly which software to use. This brings us to a massive section of the guide, the modern tech stack.
It's important to know the actual tools companies use.
If someone is walking into an interview in 2026, they cannot just talk about abstract theory. They need to know the specific, heavy-hitting tools that global companies are actually purchasing today.
The landscape has evolved rapidly. Today, the conversation is dominated by cloud-native platforms. The big three are Snowflake, Amazon Redshift, and Google BigQuery.
Let's start with Snowflake. Every data engineer talks about Snowflake. What makes its architecture so revolutionary?
Snowflake changed the industry by fundamentally separating compute from storage.
Now, let's define those terms clearly for the listener.
Storage is the memory. It is the hard drive where the data physically sits. Compute is the brain. It is the processor that does the math and runs the queries. In older traditional databases, these two things were physically locked together inside the same machine.
So if you had 10 petabytes of historical data, a massive amount of storage, but you only ran one simple report a week, you were forced to buy massive, expensive supercomputers just to hold the hard drives.
Exactly. You were paying for a giant brain that you did not need just to get the storage space. Snowflake completely separated them. The data sits in extremely cheap cloud storage. The brains, the compute clusters, are completely separate.
So how does that save a company money?
Because they scale independently. You can store your 10 petabytes for a very low cost. When the CEO wants to run a massive, complex report on Monday morning, you can click a button, instantly spin up a giant, expensive supercomputer brain, run the query for exactly 2 minutes, get the answer, and then turn the brain off.
Wow.
You only pay for 2 minutes of compute power.
That is brilliant. It treats compute power like electricity. You only pay when you turn the switch on. The guide also mentions a feature in Snowflake called time travel.
Yes, Snowflake automatically keeps hidden snapshots of your data as it changes. If a junior engineer accidentally writes a SQL command that deletes an entire production table,
Which happens.
it definitely happens. But they do not need to panic or restore from a tape backup. They can simply write a command that says, select all data from this table exactly as it looked yesterday at 4:00 p.m. Snowflake instantly retrieves the lost data. It is a massive safety net.
That alone is worth the price. Okay, next on the list is Amazon Redshift. This tool has been a foundation of cloud data for a long time. The guide says Redshift power comes from MPP, massively parallel processing. How does MPP actually work mechanically?
MPP is about division of labor. Imagine I ask you to read a library of 10,000 books and find every mention of the word ocean. If you read them one by one, it will take you a lifetime.
Because I am just one single processor.
Right. But what if you hire 1,000 people? You stand at the front as the leader node. You divide the books evenly. You give 10 books to each person. They all read their books at the exact same time in parallel.
Okay, I see.
They raise their hands and give you their individual counts. You add up their answers and deliver the final result.
Oh, so Redshift has one leader computer that takes the SQL query, breaks it into pieces, and hands the pieces down to dozens of smaller compute computers. They all scan their separate hard drives at the same time and send the math back up.
Exactly. Massively parallel processing allows Redshift to scan billions of rows in seconds. It requires careful tuning by the engineer to ensure the data is distributed evenly among the workers, but when tuned correctly, it is incredibly fast.
Teamwork on a massive scale. Next is Google BigQuery. The guide describes BigQuery as serverless. Now, obviously, Google has massive physical buildings full of real servers. So what does serverless actually mean for the data engineer?
It means the data engineer is completely freed from managing infrastructure. With Redshift, the engineer still has to make decisions about hardware. They have to decide, I want to rent exactly 10 worker nodes of this specific hardware size. They manage the cluster.
But with BigQuery,
With BigQuery, you do not choose hardware at all. You literally just paste your SQL query into the window and press run. In the background, Google's artificial intelligence instantly analyzes your question, decides it needs exactly 4,322 processors to answer it quickly, grabs those processors from its massive global pool, runs the query, and releases them milliseconds later.
so I never see the servers. I never manage them.
Never! And because of this, the pricing model changes. You do not pay per hour for a machine. You pay exactly for the amount of data your query had to scan. If your query scans 1 terabyte of data, you pay Google a few dollars. It is pure pay-per-query.
That is incredibly accessible. We will touch on BigQuery's built-in machine learning at the end of the show because that is a massive topic. But first, let's look at a tool that is highly popular right now, Databricks. The guide says Databricks uses a lakehouse architecture.
This is a very important concept. Historically, companies had two different storage systems. They had the data warehouse, which we know is highly structured with perfect rows and columns, but they also had a data lake.
What goes into a data lake?
Everything else. Massive amounts of unstructured raw data, text files from customer support chats, raw image files, continuous sensor data from factory machines. It is chaotic and lacks a strict schema.
So a company had to maintain both systems and try to make them talk to each other.
Yes, Databricks created the lakehouse architecture to combine them into one platform. They built a technology called Delta Lake. Delta Lake adds a layer of reliability and structure directly on top of the chaotic data lake. It allows engineers to run high-quality, warehouse-style SQL queries directly against the cheap, massive storage of the data lake.
It attempts to give you the best of both worlds.
Precisely.
Now, besides the storage platforms, an engineer needs tools to organize the work. The guide heavily features two specific tools, dbt and Apache Airflow. What does dbt do?
DDT stands for Data Build Tool. Remember the ELT process. We loaded the dirty data into the warehouse, and now we need to transform it. Before DBT, engineers had to write complex scripts in Python or Java to clean the data. DBT allows anyone who knows basic SQL to write transformation rules.
Now that makes it much easier.
It does. It treats SQL code like professional software, allowing teams to test their code and track changes together.
And what about Apache Airflow?
Airflow is the ultimate boss. It is the orchestrator of the entire system. In a large company, you do not just run one task. You have a pipeline of thousands of tasks. Task A pulls data from a marketing API. Task B loads it into Snowflake. Task C runs DBT to clean it. Task D updates the materialized view.
And they must happen in the exact order. If task A fails, you cannot run task B or you will process empty data.
Exactly. Airflow manages the schedule. It uses a concept called a DAG de Sede, DAAOG, Directed Acyclic Graph.
Directed acyclic graph. That sounds like advanced mathematics. Let's translate that into B1 English.
A graph is just a map. Directed means it has arrows pointing in one direction. Task A points to task B, and acyclic simply means no circles. There are no loops.
Why is having no loops so important?
Because if task A triggers task B, and task B accidentally triggers task A, the computers will loop back and forth infinitely until the entire global system crashes and burns. A DAG guarantees that the river of data only flows forward, from extraction to final reporting. If any step fails, Airflow stops the flow and alerts the engineer.
Okay, let's look at the bigger picture here. As a listener, I'm hearing about Snowflake, Redshift, BigQuery, Databricks, dbt, Airflow, Kafka. It is an overwhelming alphabet soup of technology.
It really is a lot to learn.
If I am a lead engineer at a mid-sized startup, we have very limited funds and I do not have a dedicated team of IT mechanics to manage servers all day. Which of these tools should I actually choose to build my data warehouse?
The guide offers practical advice for this exact scenario. For a smaller team without dedicated database administrators, the industry heavily favors fully managed serverless solutions. Snowflake and BigQuery are often the top recommendations.
Because you do not have to manage the hardware.
Exactly. A system like Redshift is immensely powerful, but it often requires a skilled engineer to constantly monitor the cluster, distribute the data keys, and clean the storage to maintain high speed. Snowflake handles the optimization automatically in the background. For a small team, you want to focus your time on writing good SQL and understanding the business, not acting as a mechanic for the database engine.
That is extremely practical advice. Now, we have reached the final and perhaps most important stage of our journey. Section 6 of the guide, passing the interview.
This is where it all comes together.
A candidate can memorize every technical fact we just discussed, but knowing the technology is only 50% of the battle. The other 50% is communicating your knowledge to a human interviewer.
Interviewing is a specific skill. The guide breaks the technical interview into two main areas, the SQL technical stage and the behavioral stage.
Let's start with the technical test. Usually the interviewer will open a shared screen, give the candidate a fake database, and ask them to write SQL code live. What specific SQL concepts do interviewers look for in 2026?
They want to see that you can do more than just basic filtering. A major focus is on window functions.
Let's explain how a window function works mechanically.
Let us say the business wants to know the top 3 highest spending customers, but they want to know this for every single product category. A basic SQL function aggregates everything into one massive total. A window function allows you to look through a specific window of the data while keeping the individual rows visible.
So mechanically, you write code that tells the computer, um, first partition the data by product category. Put all the electronics in one pile and all clothing in another.
Yes. And then, inside that specific window, order the customers by how much money they spent, from highest to lowest. Finally, assign a rank number to each row, 1, 2, 3, and filter the results to only show ranks 1 through 3. Writing that logic cleanly demonstrates a high level of SQL mastery.
What else do they test?
They test how you handle updating records. We discussed incremental loading earlier. In SQL, this is often tested by asking a candidate to write a merge statement, sometimes called an IPSert.
UPSUIT, a combination of update and insert.
Exactly. You have a table of existing customers and a new batch of data arrives today. The interviewer asks you to write code that compares the new data to the old data. The code must say, if this customer ID already exists in the table, UP-date their total spend. But if this customer ID is completely new, insert a brand new row. It proves you know how to safely manage data flow without creating duplicates.
That makes perfect sense. Now, assuming the candidate writes flawless SQL code, they pass to the behavioral stage. This is where tech professionals often struggle. The interviewer stops asking about code and starts asking about past projects, conflicts, and mistakes.
It can feel uncomfortable, but it is necessary. To answer these questions clearly, the guide strongly recommends using the STAR method.
STAR. Situation, task, action, result. How does that structure an answer?
It forces you to tell a logical story. If the interviewer asks, tell me about a time you improved a slow system, you do not just say, I added an index, you use STAR.
Situation. At my last job, the morning financial reports were taking 40 minutes to load, and the executives were frustrated.
Task. I was assigned the responsibility of reducing the load time to under 5 minutes without increasing the cloud computing budget.
Action. I analyzed the query, discovered it was scanning 5 years of unpartitioned history, and redesigned the tables using horizontal partitioning by month. I also implemented a materialized view for the final aggregation.
Result. The dashboard load time dropped from 40 minutes to just 12 seconds, and we actually saved money because the database processed less data.
It is a perfect narrative arc. It proves you understand the business context, not just the code. The guide also highlights a very common behavioral question: handling conflict with stakeholders.
Conflict is inevitable.
For example, the marketing department demands that a specific table be organized in a way that helps their software, but the finance department demands the exact opposite structure for their audits. How does the candidate answer that?
The guide introduces a prioritization framework called the Moscow method. It helps organize conflicting demands.
Moscow. Spelled like the city, but it stands for must have, should have, could have, won't have.
Yes. You explain to the interviewer that you would bring both teams into a meeting and categorize their requests. You agree on what the system absolutely must have to function legally, perhaps finance's audit trail. You identify what it should have to improve marketing speed. You list what it could have if there's extra time, and you clearly define what it won't have in this current version.
I understand the framework, but I am going to challenge this on behalf of the pure engineers listening.
Okay, let's hear.
Why does an engineering manager care if I know how to run a meeting using the Moscow method? If my Python scripts run perfectly and my SQL is optimized, shouldn't that be enough to get the job? Why is conflict resolution part of a technical interview?
It is a valid frustration, but if we connect this to the reality of the business world, a data warehouse does not exist in a vacuum. It is a service tool. The entire purpose of the engineering team is to provide accurate answers to human decision makers. If you build a perfectly optimized, flawlessly coded Snowflake schema, but it contains data organized in a way that the marketing team cannot understand, or it fails to answer the CEO's actual questions because you refuse to communicate with them, your perfect code is entirely useless to the company.
Ah, the code is only as valuable as the decisions it supports.
Precisely. A senior data engineer must be able to translate human business problems into technical database architecture. You cannot do that without communicating effectively with non-technical stakeholders.
That is a powerful realization. Another major behavioral question involves disaster response. The interviewer will ask, tell me about a time a critical ETL pipeline failed during peak business hours. What did you do?
They are testing your maturity and your operational process. They want to see that you do not panic, and more importantly, that you do not hide the mistake.
What is the correct sequence of steps to describe?
First, identify and mitigate. You explain how you used Airflow logs to instantly locate the failure. Second, you implemented a temporary fix or reran the pipeline to get the data flowing again because the business is actively waiting for it.
Third, communication. You sent an immediate message to the data analyst explaining that the data is delayed, why it happened, and when it will be fixed.
And finally, the most critical step, root cause analysis. You explained to the interviewer how, after the fire was out, you spent 2 days analyzing exactly why the code broke and how you wrote new automated data quality tests to guarantee that specific failure can never happen again.
You show that you learn from disasters. The guide wraps up with some final practical tips. It advises candidates to continually practice SQL challenges online to build small, real-world portfolio projects. You can literally sign up for a free BigQuery tier and process public datasets to prove your skills. And to always ask the interviewer intelligent questions at the end.
That last point is crucial. When the interviewer says, "Do you have any questions for me?" never say no. Ask about their architecture. Ask, "What is the biggest data quality challenge your team is fighting right now?" It proves you're already thinking like a working member of their organization.
It shifts the dynamic from a test into a professional collaboration. Well, we have covered an immense amount of ground today. Let's briefly retrace our steps. We started by building the foundation, understanding why the rapid transactions of an OLTP kitchen are fundamentally different from the deep historical analysis of an OLAP library.
We examined the architectural blueprints, comparing the fast, redundant star schemas against the highly controlled, normalized Snowflake schemas.
We tackled the messy reality of data ingestion, comparing traditional ETL water filtration against modern ELT staging areas. We learned how to find needles in haystacks using partitioning and indexing, and how surrogate keys protect the system from the chaos of the real world.
We explored time travel, detailing how slowly changing dimensions, especially type 2, preserve a perfect, unalterable history of the business.
We looked at scaling up, trading perfect real-time freshness for the incredible speed of materialized views. We surveyed the massive tools of 2026, from Snowflake's separation of compute and storage, to Redshift's parallel processing, to BigQuery's serverless AI. And finally, we decoded the interview itself, from window functions to the star method.
It is a complex, deeply logical discipline. The Data Camp Guide provides a robust, comprehensive map for anyone trying to navigate this profession.
It is an incredible resource. But before we finish today, I want to leave you, the listener, with one final provocative thought to consider, something outside the standard interview questions.
I always enjoy these. What are you thinking about?
Throughout this entire hour, we have defined the data warehouse as a library, a perfect historical record of the past. We use SCD Type 2 to preserve what was. We use materialized views to summarize what happened. But earlier, when we discussed Google BigQuery, we briefly mentioned BigQuery ML, the integration of machine learning algorithms directly into the massive compute engines of the warehouse.
Yes, writing SQL to train predictive models on the data without moving it.
Exactly. So if we connect this to the bigger picture, as these compute engines become increasingly powerful and deeply integrated with artificial intelligence, what if the core function of the data warehouse is shifting? What if it's no longer just a passive library recording history? If the system can instantly analyze 5 years of global sales patterns and automatically generate highly accurate predictions about user behavior for next week, the warehouse becomes a living prediction machine.
That is a profound shift in perspective.
If the library starts actively writing the books before the events even happen in the real world, what does that mean for the career of the data engineer? Perhaps by 2030, an engineer will not be interviewed on how well they store the past, but on how accurately their architecture can compute the future.
It suggests the data engineer will evolve into an architect of foresight. That is a fascinating frontier to watch.
It truly is. Thank you so much for joining us on this deep dive into the mechanics and architecture of data warehousing. We hope you discovered new concepts, understood the logic behind the technology, and feel completely prepared to confidently answer those interview questions. Stay curious, keep exploring the data, and we will see you on the next deep dive.